In this lesson, we danced all class period, making sure that we're ready for our math parties and know how we can describe the end behavior of polynomials. In your head, run through the dance move, even, odd, odd. That's going to be so helpful when we describe the end behavior of these polynomials. And when we're talking about end behavior, remembering what happens as x gets really positive, when it gets really big, or what happens when x gets really negative, when you have really big negative numbers. So as I go to infinity and as I go towards negative infinity, what's happening to my function? So without using the graphing calculator, describe the end behavior. So when we describe the end behavior, we look at two things. We look at the degree and ask ourselves, is it even or odd? And then we look at the leading coefficient and say, is it positive or negative? So the degree is the highest power, so in this case it's the x to the fourth term here. So we have an even degree and a negative leading coefficient. Which means if I run through my dance moves, even, that's the second one. So if I'm describing the end behavior graphically, I don't know what happens in the middle of this function, but that happens. So I say, as x approaches infinity, as x gets really positive, my functions are going down towards negative infinity. My y values are approaching negative infinity. That function is just plummeting down. Then they're getting very negative. And as x approaches negative infinity, if I look at the other side, what's my left hand doing? My function is still approaching negative infinity. Those values are going down without limit. They just keep going down forever. So this is how we describe the end behavior using words. We look at the degree and the leading coefficient. So for g of x here, again, it's written in standard form, so it's that first term. We have an odd degree and a positive leading coefficient, which means if I run through my dance moves, even, odd, it's the third one, which means I don't know what happens in the middle, but that's what's happening on the ends. So as x approaches infinity, my y values are going up. F of x is approaching positive infinity. It never ends, they just keep getting really big. And as x approaches negative infinity, what's happening to my y values? They're plummeting down. So f of x approaches negative infinity. That's how we describe the end behavior using a verbal description. Sketch a graph of the function. So sketch, I don't want to use my calculator here, I just want to sketch it by examining the end behavior, the leading coefficient, and the zeros of the function. So the end behavior, well, I need the degree and the leading coefficient here. So my leading coefficient is 2. I have a positive leading coefficient, it's 2. What degree is this? Well, I have 1, 2, 3, 4 factors. Notice I have 1, 2, 3, I have 2 of those, so I have 4 factors, which means I have an x to the fourth polynomial. So I have an even degree, which means if I run through my dance move, even degree positive is my first dance move. My function looks something like that. I know what happens as the end behavior of my function. And the zeros, well, the zeros, it's already factored. That's easy. I get x equals -1, x equals 3, and x equals -5. I just applied the zero product property here. But x equals -5 has a multiplicity of 2. So it's going to be tangent to the x-axis. The graph is going to touch the x-axis and then turn around. So I've got -1, 3, and -5. So I know my end behavior looks something like this. I now know what happens at the middle. I go down to -5, and I touch it and turn around because I have that even multiplicity. I have that repeated factor there. I cross through -1, and I cross through 3, and that's the sketch of my function, y equals f of x. So by using my end behavior and my zeros, we can accurately sketch what these functions look like. Now, if you go to Desmos or on your TI-84, graph this function and change the window around, you're going to get something that looks like this. Number 3, the following scatter plot represents the data from a study produced by the Center for Transportation Analysis. The study observed a car's speed in miles per hour and also recorded the car's fuel economy in miles per gallon. So we inputted miles per hour, we're outputting miles per gallon. Determine if the polynomial function that models the data would have an even or odd degree. Well, if I was to sketch a polynomial through these points here, that's what my polynomial would look like. And since the end behavior, as I approach infinity and negative infinity, they're both going the same way, I'm going to have an even degree. Because as x approaches infinity and x approaches negative infinity, f of x is always approaching negative infinity. It's going down. They're both going in the same direction, so that means it's an even degree. Is the leading coefficient of the polynomial that can be used to model this data positive or negative? Well, think of your dance moves, even positive, even negative. They're both going down, so the leading coefficient is negative because f of x is approaching negative infinity. So my end behavior is I'm approaching negative infinity, so that means the leading coefficient is negative because I have that even negative first term. Number 4, describe the end behavior of the polynomial of the graph of y equals f of x shown below. If f is a polynomial, determine if the leading coefficient is positive or negative, and if the degree is even or odd. So as x approaches infinity, what's happening? As x approaches negative infinity, what's happening? What's happening to my function? Where is it going? Well, as I approach infinity, as I get really, really big on my x-axis, my function is plummeting downward, so it's going towards negative infinity. And as I approach negative infinity in my x direction, as my x's get really negative, my function's going skyward up, so it approaches infinity. Running through my dance moves, this is an odd degree because they're not going in the same direction, with a negative leading coefficient. Not too bad. Number 5, we have to think here a little bit. Can you sketch a graph of an odd degree polynomial with no x-intercepts? Explain your reasoning. So all I know is I have an odd degree, which means my end behavior is one of two things. I can have that end behavior, or I can have that end behavior. Well, can I sketch one with no x-intercepts? Well, here's the thing. If it starts negative and ends positive, what's going to have to happen at some point? Based on the end behavior, the function has to cross through the x-axis. And behavior, the function has to cross through the x-axis. This point is an x-intercept. That point is an x-intercept, regardless of what happens, as long as I resist it for as long as I want. At some point, I'm going to have to cross through the x-axis to have that end behavior. This implies all odd degree polynomials have one real zero. At least one, sorry. Have at least one real zero. You have to have one based on the end behavior. At least one real zero. So this implies all odd degree polynomials have at least one real zero because I at least once have to cross through the x-axis. It doesn't have to as many times as you want it to, but it has to happen once. So just have to think a little bit about the end behavior, that they're going in opposite directions. You have to cross through the x-axis at some point. So hopefully you learned something from this lesson about graphing polynomials. If not, you at least have cool new dance moves to use at your next math party.